Okay, so we have been talking about the Dd0 transformer modeling. So far, we have only derived the equation for IA, that is the phase A current at the primary side. So let us continue with that. So this is the diagram and as well as the phasor diagram what we have drawn in the last class. So with this, let us continue. So then IB, we can write that IB is equal to IBC minus IAB, and also we can write down that IB is equal to IB is equal to IBC minus IAB. So from this, this plus this is equal to this IBC minus IAB. So IBC is nothing but Y into VBC minus BBC, Y into VBC minus BBC, and IAB is Y into AB minus V. So therefore, Y, let us take common. So VB minus V capital C minus V small c plus V small c, and then minus V capital A, then it is minus also plus V capital B, then this is also minus, so plus V small a, and this is minus and plus minus, so minus V small b. So this becomes Y into minus VA plus 2VB minus V capital C plus VA, then minus 2VB plus VC. So this is equation 2. I capital C is I capital C. I capital C is ICA minus IBC. So this plus this is equal to this. So ICA minus IBC. So it would be ICA ICA is Y into V capital CA minus V small ca minus Y V so we take Y common, minus VB, then plus V capital C, then plus V small b minus V small c. So it becomes Y into minus VA minus VB plus 2V capital C, then plus VA plus V small b minus 2V small c. So these are the three primary side currents. Now let us look at the secondary side currents. For the secondary side currents, IBA is equal to IA plus IAC, right? Because this current is IAC, so IBA is equal to, now IBA at the secondary side. IBA is equal to IA plus IAC. So that means IA is equal to IBA minus IAC. Now IBA is equal to I capital AB. So that means IA is equal to I capital AB minus I small s is I capital CA. IAB minus ICA is, we already seen, is IA capital. Similarly, IB would be equal, ICB is equal to IB plus IBA. So IB is equal to ICB minus IBA. IB is equal to ICB minus IBA. See, ICB minus IBA. ICB is IBC and IBA is IAB. So IBC minus IAB. IBC minus IAB is IB. And IC is given by IAC minus ICB. IAC is given by ICA and ICB is IBC. So that is equal to I capital C. So this is equation 4. So you see DD is also very easy. So now we are ready. So then therefore our model would be, therefore IA, IB, I capital C minus IA. V small a, V small b, V small c. Now, equation of IA. 2 minus 1 minus 1 minus 2 on 1. Okay. 2 minus 1 minus 1 minus 2 1 1. Correct. 2 minus 1 minus 1 minus 2 on 1. IB minus 1 2 minus 1 minus 1 2 minus 1, and then 1 minus 2 1, 1 minus 2 1, I capital C, minus 1 minus 1 2, minus 1 minus 1 2, 1 1 minus 2, 1 1 minus 2. Minus IA means minus I capital A. Minus I capital A means everything should be minus. So minus 2 1 1. So it is minus 2 1 1. And 2 minus 1 minus 1. 2 minus 1 minus 1. Similarly, it would be 1 minus 2 1 minus 1 2 minus 1, 1 minus 2 1. Let's see, 1 minus 2 1 minus 1 2 minus 1. Okay, and it is 1 1 minus 2 1 1 minus 2, and then minus 1 minus 1 2. So this is the matrix. So if we do partition, so this is y1, 2 3 4. As usual, we can see that y2 and y3, those are transposed to each other. So minus 2, so 1 minus 2 and 1 1 minus 2. So y2 and y3, those are transpose of each other. So this is the way how to model a Dd0 transformer. By the same method, we can model any ddx where x is 2 4 6 8 10. Now for obvious reasons I am not doing it, you please carry on, because it should be now pretty much straightforward. We have shown several examples of how to model different types of transformer, three-phase transformers. Of course, we have not considered any unusual types of winding. We have considered the most common types of winding, that is Y and D, either at the both side, any combination. But we have also considered that how to take into account their group. So out of all these modeling, the common thing what we can find out is that if I have a transformer, and this is the primary winding, VA, VB, VC, this is a transformer, three-phase transformer, and this is I capital A, I capital B, I capital C. So this is the primary side, so this is primary. Then I have at the secondary side, this is VA, VB, VC, and the current are also entering this. Please note, our all models are current are entering the transformer. So this is IA, this is IB, this is IC. So this is my secondary side. So with this, when the windings, when the currents at both the sides are entering the transformer, we can represent them as I A B C, and I A B C is equal to Y1, Y2, Y3, Y4. V A B C, V A B C. So this is the model of a transformer where Y1, Y2, Y3, Y4 are the admittances matrix, which are each of them is 3 cross 3, and Y2 and Y3 are always transpose of each other. And so then therefore this entire matrix is essentially 6 cross 6, obviously, because at the current side there are 6 currents and at the voltage side there are also 6 voltages. So then therefore the combined admittance matrix would be 6 cross 6 matrix. But the elements of these 4 submatrices, that is y1, y2, y3 and y4, they would be different for different types of transformer connection as well as for different groups. That is, even if I have same type of transformer connection, for example, let's say yd, but for let's say yd1 and for let's say yd5, these matrices y1, y2, y3 and y4 would not be the same. So then therefore for each type of connection as well as for each vector group, we need to find out these 4 matrices very carefully. But we have already shown the method for finding out these matrices for any type of transformer connection as well as the vector group. So then therefore now it should not be any problem. So with this we have now finished our modeling part. So far we have done the modeling of the series impedance of a transmission line. So far what we have modeled? We have modeled that series impedance of the transmission line, then shunt charging susceptance. We have also modeled that of a transmission line susceptance. So these are all basically for transmission line. That we have modeled, and we have already seen that this series impedance is for a 3-phase transmission line. It is always a 3 cross 3 matrix. Usually this 3 cross 3 matrix is basically a full matrix, that we have also got this off diagonal elements, that is there is a considerable amount of mutual impedance among the phases. There would not be any kind of mutual impedance only if this line is fully transposed, but otherwise there will be some amount of mutual impedance always. So it is generally represented by a full 3 cross 3 matrix. It is not at all a diagonal matrix. Similarly, we have also looked at the basically the shunt charging susceptance, and we have also seen that this shunt charging susceptance of a transmission line, that is of a 3-phase transmission line, 3-phase line, is also a 3 cross 3 admittance matrix. And what we will do is that essentially this is nothing but a capacitance matrix. We have already seen that this admittance matrix is essentially nothing but a capacitance matrix. So then therefore this matrix can be represented by an equivalent susceptance matrix. And as we do in the case of a balanced transmission line, we will represent every transmission line of we will represent every three-phase transmission line by its equivalent pi model, where the series part would be represented by its series impedance matrix, and the shunt part at both the sides would be represented by half of the shunt charging susceptance matrix. So then therefore it would be an equivalent pi model of a transmission line. And then of course we have already modeled a transformer. We have seen just now that for a last few lectures that for a transformer this is essentially modeled by an 6 cross 6 matrix, but then this 6 cross 6 matrix can be partitioned into 4 3 cross 3 matrix. Out of these four partitioned 3 cross 3 matrices, two matrices are actually transposed to each other. So with this we finish the essentially the modeling part of individual components. Now from the next lecture onwards we shall now concentrate on to model and transmission network in which we can have any number of lines, any number of transformers having any kind of winding. Of course, when we are talking about any kind of winding, we would be only restricting ourselves to the most common types of windings, that is the YD and the associated vector groups among them. And then we will see that how to represent any transmission network consisting of any number of transmission lines and any number of three-phase transformer. Please note, whenever henceforth whenever we will be talking about the transmission line, we are always talking about three-phase transmission line, and also when we are talking about transformer, we are always talking about three-phase transformer. So we will be looking into that how to model a transmission network when all the lines are unbalanced three-phase lines, may be transposed, may not be transposed, as well as we have got any number of three-phase transformers. So we will first start with the process of finding out the Y-bus matrix of a three-phase transmission line. Then we will embark on the power flow analysis of a three-phase transmission network consisting of lines, transformers, as well as the generators. So we shall embark on this exciting journey from the next class onwards. So today, thank you. Goodbye.